talk. So in this talk, I'm planning to present a joint work with Cecilia Salgado, in which we studied a construction of locally recoverable codes having the availability property from a family of fibered surfaces. So my plan is to start by just recalling some definitions and fixing some notations on locally recoverable codes from varieties over finite fields. And then I will tell you something about our constructions and about the parameters of the codes that we obtained. So to start off, in these slides, I will usually denote with C a linear code over the finite field with Q elements, Fq of length n, dimension k, and minimum distance d. So just to introduce what are locally recoverable codes, so we will say that C is a locally recoverable code, or simply LRC for short, with locality R, if any symbol of any code word can be recovered from a subset of R many other symbols of the same code word. And this is what we call a recovery set for our initial symbol. So why do we care about this kind of codes? So over the past decade, there's been quite some interest in these codes, mainly for applications in distributed data storage. Because there you can imagine that the setting is like, it's a setting in which like you encode your data, and then you store it in a way which is like spread out across multiple servers. So your code words are literally like stored in chunks in the different servers. And a very typical scenario is that of a server failure. So maybe at some point, a server just breaks down or becomes unavailable, and then suddenly you have code words which maybe have one erasure, and you want to be able to recover this missing symbol. And the point is that generally, if you just use a code without the locality property, then what happens is that you have to access k many, so as many as the dimension of the code, other information symbols, which can be very inefficient if the code is a very high dimension. But if you're using an LRC, and here, so we're going to require that the locality parameter is like much smaller with respect to the dimension, then this is quite nice because if you're using an LRC and you lose a symbol, then the idea is that, okay, maybe I can actually recover this missing symbol by only using a small portions of other symbols of the code words. So in practice, this would mean I only need to access very few other servers, which makes the process like, in practice, much faster and much less expensive. So this is why there's been quite some interest on this kind of codes. But of course, so there are some downsides, and in particular, let's say, things can go wrong in many ways. So what can happen is that, well, you lose a symbol, but then you might also lose some additional symbols that are part of the recovery set of your symbol. And this is bad because when you use an LRC, so you really need all the symbols in a certain recovery set to perform the recoverability procedure. So this calls for like adding some extra layers of data protection. And so two famous constructions that people use is adding what is called the hierarchy and what is called the availability. And this second one is what we're going to look into today. And an LRC has availability A simply if like any symbol of any code word has a many possibly disjoint recovery sets. So the idea is like, okay, I missed a symbol, I want to try to recover, but maybe I'm unlucky, and I also missed some symbols in one of the recovery sets. So what I do is that, okay, maybe I can look at another recovery set which I have, and maybe this recovery set is fine. So that's the idea. And yeah, so there are many different constructions of locally recoverable codes known in the literature, and in particular, several of them have been obtained as algebraic geometry codes. So I'm just going to recall something from the theory of algebraic geometry codes, because this is also the kind of constructions that we studied in this work. So here, this is the notations that I'm going to use. So we fix some quasi-projective variety over Fq. And then, so we pick a set, which we call S of n distinct rational points of our variety, so P1 to Pn. And then we also pick a finite dimensional Fq vector space, which is a subspace of the Fq rational function field of our variety. And then what we do is we want to define this evaluation map, so from our vector space P to Fqn. And this map simply sends functions in this vector space to the n tuple given by the evaluation of such functions at the points P1 to Pn. So of course, one here needs to be a bit careful in the sense that for this map to be well defined and to actually make sense in the first place, you need to make sure that the points that you pick and the functions that you pick are such that these functions can actually be evaluated at these points. So you don't want the functions to have poles at those points. But so provided that you make the choice of S and the choice of V carefully enough, then it turns out that this map is actually well defined, and it can also be shown that it is linear. So in fact, what is called the algebraic geometry code, or simply the AG code for short, associated to our variety and to the set S and the vector space V, is the image of this evaluation map in FQN. So it's just a linear subspace of FQN. And so AG codes are interesting for many reasons. And for instance, they are interesting because it turns out that several of their properties can be either, well, deduced or at least estimated from properties of the underlying variety. And in fact, this is also why constructions of locally recoverable codes as AG codes turned out to be quite nice, because then one, let's say, if one chooses nicely enough the variety, then can actually obtain constructions of like LRCs with availability or with a hierarchy or with other properties. And is also able to say something about other parameters like the minimum distance or the dimension. Okay, so in this slide, I collected just some names of people that have recently worked on locally recoverable codes constructed as AG codes. Here, I only put these like to give you an idea of like how many people have been working on this lately. So to give you an idea of also like how many different constructions are out there. And this is by no means a complete list. So if you have been working on this and your name is not there, I apologize. This is just like a list of recent literature I had been looking at for our work. And yeah, it's really just to give you an idea that like there are really many different constructions coming from curves, coming from surfaces. And in particular, so for our work, it was of inspiration, a recent paper that came out last autumn, which is from Aguilar, Alvarez, Ardila, Ocal, Rodriguez Sevilla, and Barilli Alvarado. Because in this paper, the authors studied some families of LRCs with the availability properties, and these codes turned out to have like quite interesting properties, also with regarding to the minimum distance and also asymptotically. Okay. Yes, so to set the stage for our construction, so this slide is like just intuition. So let's say just geometric vibes. So as I was mentioning in the paper of the authors I mentioned before, they obtained these LRCs from products of affine or projective spaces. And in our case, so what we tried to do was just to put ourselves, well, in a three-dimensional affine space. And to try to look at certain like surfaces which had some nice properties. So the idea is sort of the following. So here you can imagine your rectangle as like a surface in a fine 3D space. And then, so here, these are just like two lines. So here we're going to think projectively at some point, but for now, just for simplicity, let's think affine. And so two things, let's say the two things we have to do to start constructing the codes is to select a set of evaluation points and then to select a set of evaluation functions. So the idea for picking the set of evaluation points is something like this. So we would like to have some surface, and we would like this surface to have two distinct vibrations, so just two distinct maps, basically from your surface to lines, in our case. So we're going to aim for like LRCs with availability 2. And the idea here is that, okay, so every point of our surface will lie both on a fiber here, which I'm going to call vertical just to fix some notation. So every point is going to lie on a vertical fiber, but also every point is going to lie on a horizontal fiber. And so we want to be able now to sort of control which points we are taking, so that we would like to have sets of points that all lie on the same horizontal fiber, and then also we would like to have sets of points that all lie on the same vertical fiber. So how do we do this? So we look actually at a curve or like we would like to find some curve which lies on our surface. And this is what should help us to select these points. In the sense that what we actually do is we're gonna pick points that specifically lie on this curve. And then what we do is we look at the intersection of this curve, which is what we call a multisection. So it's simply like some curve that intersects each fiber, both vertical and horizontal, multiple times. And so what we do basically is that when we pick a point on our curve, then we also want to pick all the other points lying on the same horizontal fiber and on the curve. And in the same spirit, we also want to pick all the other points that lie on the curve and on the same vertical fiber of the point that we've picked. So this is more or less the spirit, because the idea is that then we might be able to devise some recovery procedure, which basically, let's say that at some point we lose the evaluation that we have here, then maybe we can use the evaluation that we have at these other points to recover this, but also maybe we can use the evaluation at these other points to recover this point. So this is the sort of geometric idea. More concretely, we started actually with these surfaces. So here I'm going to fix some parameters. So R is going to be some odd integer larger than or equal to 3. We assume that we are working over a field of characteristic different from 2. The reason for this will not be evident from these slides, but we need it at some point. And also we require that Q is congruent to 1 mod R plus 1, and this will be evident from the slides. Okay, so we consider basically a family of surfaces whose equation look like this. And then what we do is actually nothing so special, because then on this surface, we can consider this curve. This is clearly a curve contained in the surface. And now here I'm going to use this sort of funny notation. Instead of saying like A3, I'm saying A2 cross A1, but this is just really to keep in mind that when at some point we will compactify this, we will actually compactify this in P2 cross P1. Okay, so this surface sort of behaves like in the picture I showed you before, in the sense that there are two fibrations that you can see, one over the T line, so you can fix T, and then you get a bunch of elliptic curves here, or you can fix X, and here you get a bunch of other curves of degree R plus 1. So these are the two fibrations that we see from here. And so what we want to do is to select the evaluation points, to pick some points from this curve here, which is a multisection from the fibers of both fibrations. And so what we do, well, first observation is right here, you plug in this value of y in here, you end up with this nice equation. So basically, you can now translate the problem of like how do we pick the points on these curves. Well, why don't we look at the function field of the curve defined by this equation, and we look at rational places. And this will work quite nicely, because actually we are going to disregard singular points, and we're working really with rational points. So we can translate this problem in a function field language. And more precisely, we are interested in understanding these two extensions. One is going to be nicer in the sense that you can see from the equation that this is actually a nice Kummer extension. This other extension is going to be less nice. But still, the idea here, it's basically, so this property basically of picking points so that you have exactly, so when you have one point, you also have a bunch of points which are exactly as many as the degree of the multisection minus 1 on a horizontal fiber and the degree of the multisection minus 1 on a vertical fiber, actually translates perfectly in basically picking points on your curve that correspond to places here that lie over completely splitting places both in this extension and in this other extension. And so a first step that we need to do to make sure that actually such places exist in the first place, sorry about the pun, that was not intended, is to extend the constant field. Because otherwise it is not necessarily true that we are able to find not even one place having this property. So in the case R is equal to 3, we need to extend the constant field to be Fq to the R plus 1. In the case R is larger than 3, we extend it to Fq to the R times R plus 1. And then, okay, then the situation that we want to study, if you can actually translate it in, so looking at this polynomial, this is just the polynomial I showed you before defining this function field here. Now I just plug in some variable instead of x. And what we need to understand is basically, okay, I need to find like at least one value in principle in Fq star such that this polynomial splits completely into r plus 1 distinct linear factors, because this will give me exactly a place here which lies over something that splits completely here and also that splits completely here, and not that this part, in a sense, will come for free, in a sense that since we assume that Q was congruent to 1 mod r plus 1, the idea is that if we find one t-bar that works well, we're actually going to find r plus 1 automatically. So yeah, this is the splitting of this polynomial basically is what we need to figure out. But so yeah, provided that one does this, then one can actually explicitly find the evaluation points. Here I just put in the equation just to say, okay, we can just write them down in this way. There is a constraint here actually on the cardinality of the field, because since we find these values of t-bar in blocks of r plus 1, and we're gonna like find them iteratively in this kind of blocks, so let's say b many blocks, then we need the field to be at least the b times r plus 1. All right. Okay. So the length of our code is going to be exactly this. And then, so the other step that we need is define a set of evaluation functions. And here I just put the picture to keep in mind like what is happening on a geometric point of view. And I just fixed this notation to say, let's say, okay, this is basically points in the horizontal recovery set. So this would describe the points here, and this set P describes these points here. All right. So in this setting, the functions that we choose are actually just polynomials into variables, t and x. So they look very, very simple. And we have this constraint on the degree that actually will be useful for the recovery procedure later. And so with this space, also one can show that the evaluation map is in fact injective, so that in fact the dimension of the code is really just the dimension of this as a vector space over Fq. So we get something that is R square. Okay, so is this code actually locally recoverable? Well, it is, and I'm going to be just faster on this. But the idea is that with this construction, we actually get some horizontal recovery set and some vertical recovery set. And here, the idea of this proof is really just linear algebra, in the sense that because of how we picked the points on the curve and with this particular structure, it turns out that, for instance, let's say that we lose one certain point and we want to use the vertical recovery set to try and recover it. Well, but now all the points in this vertical recovery set have exactly the same t coordinate. So this means that we can nicely write down the evaluation of our of the function that was giving the code word that we're looking at. If we look at it restricted on the recovery set, we can write it in this nice matrix form, where this, well, now this is not a square matrix yet, but now we're going to get rid of the evaluation we're missing, and we're going to get rid of the first row here. And now this means that like we end up with a nice van der Monde matrix, and we can invert it because points lying on the same vertical recovery set have the same t coordinates, but pairwise distinct x coordinates. So there's nothing very special going on there. And just let me just quickly comment on this. So we can also give some bounds on the minimum distance of these codes. So there is this is an upper bound which is of singleton type given by Tamobarg and Frolov in this paper. To give a lower bound, basically what we do, and this is why we compactify in P2 cross P1, is basically we try to look at some points that are not evaluation points, and we try and understand if the functions that we are chosen actually have a high vanishing order there, because then this means, okay, we can, if they vanish a lot at those points, then they will vanish less on our curve. And so we estimate actually how our functions vanish at the places that correspond to the pole of t. And this leads you to this picture, and I'm closing on this. So basically, we obtained then some algebraic conditions, and the picture is the following. So turns out that if we are in the condition that -1 is a square in the field K, then actually we end up with codes that are optimal with respect to the Thamo-Berg-Frolov bound. And on the other hand, if -1 is not a square, then we end up with codes that are not optimal, but we are still able to give some sort of lower bound. And just to conclude, oh yes, so this is the preprint is not an archive yet because there's partially some work in progress to do. And but besides, questions that I think would be interesting is of course try and do something like this with different surfaces, because of course we just choose one that was nice enough, but there's plenty to do. And also possibly study the asymptotic parameters of these codes, although it's not super clear to me yet how to do it. Yes. So thanks a lot for your attention.
Thank you very much, Lara. Any questions or comments?
Very much for this beautiful talk. I have a very naive question. Are there any diagonal recovery sets?
Sorry?
In the picture on page 6.
Yeah. Oh, yes.
Vertical and horizontal.
Yes.
Are there any diagonal?
Oh, yes. So, okay, this is very, I'm sorry, because this language is very fishy in a sense. Like, it was easy to look at, let's say, one fibration as horizontal and one as vertical, but like you can call them however you want. But maybe to give you the idea, here it's really important that like the points in one recovery set lie on a same fiber. Of one fibration.
Oh,
so,
okay.
I mean, in principle, if you have, let's say, if you have 3 fibrations instead of 2, then yes, so maybe you could have, let's say, a third fibration, which you could call a diagonal fibration. And then you could play this game if you're able to also select points lying on the same fiber also of that fibration.
Okay.
So
okay. Thank you so much.
Yeah.
Any other question?
Thank you, Lara, for this nice talk. I just wanted to ask you, so in this case, you have a variability 2, yeah? So as she asked, if you want to get larger variability, so what could be a nice strategy to go to a higher dimensional stuff? Or I don't know, it's just a question.
No, that's interesting, in fact. So I'm not sure, to be honest, of what the best strategy could be. I think so. So to be fair, one reason why we initially started to look into these surfaces, it's because, well, maybe not all of them, but at least some of the surfaces in this family are like K3. So for some of them, you might be able to prove that they actually admit multiple fibrations, actually multiple elliptic fibrations. So an initial idea was to try and see, okay, maybe we can find one which actually has plenty of these fibrations, and then we can play this game with like more availability. But then it was actually very difficult to find, let's say, explicit examples, like explicit equations, where we were also able to, because you need to have an explicit equation of the surface and then also to have explicit equations of the fibrations. And then so it gets much messier. But I think in principle it's possible, like to either look for surfaces which have like many more fibrations, or maybe, to try to go to higher dimension. Because I think maybe that's probably easier, or I don't know, but to my intuition that could be easier. But
Thank you. Thank you.
I'm afraid we have no time for more questions. So let's thank Lara again.
E a pontinha no meio.
So moving on, it's a pleasure to present Luciane Kos. She will talk about linear complementary pairs of AG codes and linear complementary dual AG codes. Thank you, Luciane.
Thank you. So I'm going to talking about linear complementary pairs of AG codes and LCD codes, linear complementary dual codes. This is a joint work with Alonso Castellanos from Uberlândia and Adler Marques from University of Rio de Janeiro too. And well, let's go for the introduction. So first, why to study this kind of codes? Like about 10 years ago, people proved that having linear complementary pairs of codes could be used to prevent attacks like Trojan attacks. There are like 2 or 3 papers from 2015 on this, like Claude Carlet did also. Okay, so this is why we are going, and we are going to study like AG codes of this type. So we have the, well, FQ, the finite field. So a code says just a vector subspace of FQ to the n, a vector subspace over FQ. And then you have the 3 parameters. N is the length, so it says you the size of where you live, FQ to the n. And then you have K, that's the dimension of C as a FQ vector space. And you also have D, the Hamming minimum distance. So we have the simplest bound relating these 3 parameters is the singleton bound. We know that Q plus D is at most n plus 1. So one way to think if you have a good code or not, you just look to the difference that we call usually the singleton defect, n plus 1 minus K plus D. So smaller is the singleton defect, better in some ways the code. Okay? So, and well, the dual of a code is just the dual, like as in linear algebra, using the normal inner product, Euclidean inner product. Okay? And so, well, we say that a code is self-dual if the orthogonal is itself. And we say that a code is isodual if the orthogonal is just a vector, like a vector with no 0 coordinates times your code. So we relax a little bit the first definition. And why is it good? Well, it's good because if you have the parameters of a code C, actually the parameters of the code X times C are still the same. So you don't lose anything on about the code being good or not. So you don't lose things. And well, this kind of codes have been studied a lot. So I put also some names. Most of them are here in the conference that have worked on AG codes or self-dual codes or iso-dual codes or flags of codes. Okay, so we have here some names. And well, the one I'm going to present today is like we are going to study linear complementary dual codes. So it means that if you do the direct sum of the code with its orthogonal, you have the whole space. Okay? And we say that a pair of codes is linear complementary pair if the direct sum gives you everything. So of course, if you have a pair, and if your second code D is just the orthogonal of C, then you have an LCD codes. So here I'm going to present these codes, but AG codes, algebraic geometric codes of this type. So at first, we are going to construct some pairs. And from these pairs, we are able to prove that sum of the pairs, actually, you can get LCD codes. Okay? So we need to define what are algebraic geometry codes. I think Lara, she already did that, but well, more or less the same. You have been using, so Lara was using any vector space. We are going to use Riemann-Roch vector spaces here to define. So you take your function field of genus G. So I'm thinking about a function field of an algebraic curve. Okay? of genus G. So you fix any divisor D that is the sum of pairwise distinct rational places. So you take any different points on your curve, okay, rational ones. Fix a divisor G that the points on G are not on D. And the algebraic geometry code is just the evaluation of functions living on the, where is the, here. The functions living on the Riemann-Roch space associated to the divisor G, and then you compute, evaluate the functions here. So evaluation is always linear, so the image of a linear function, you have a vector space. So our code is just the image of the evaluation function, okay? And, why these codes are so important? Because since we have an underlying algebraic curve related to them, we can say something about the parameters already. Okay, so we can say like that we can easily see that the dimension of the code is just to compute the dimension of the Riemann-Roch space G minus this, the dimension of the Riemann-Roch space associated to G minus D, and we also have a lower bound on the minimum distance. So age codes are associated with error correcting codes, and the people have been working 20 years trying to improve this minimum distance. That can be done using codes in 1 point, 2 points, more points. Okay? Okay, so we have the codes. So what is good about age codes is that the dual of age code is still an age code. So I can really talk about LCD age codes. Okay, you have an age code, you take the dual, it's still an age. But theoretically, it's still an age code. But the problem is that if you want to really compute the dual of your code defined by D and G, you need to find a certain differential on your function field with certain properties. And that is the tricky part or hard part. Okay? So, I just said this to determine the dual, we need the differential. And, I'm going to present, constructions based on the existence of non-special divisors. So let's start in defining what is a non-special divisor. So a non-special divisor in your function field is a divisor such that the dimension of the Riemann-Roch space associated to A is just the degree of the divisor plus 1 minus G. Okay? And, you know by Riemann-Roch theorem that if the degree of the divisor is large enough, is larger than 2 times genus minus 2, it's always non-special. Okay? And we can, it's easy to see that if A is non-special, if this is, okay, then we have that the degree of A has to be at least G minus 1. So you have non-special divisors from degree G minus 1 to degree 2G minus 2. And we want the ones with a small degree. So degree G minus 1 or degree G. Okay? And, so before that, I just need 2 definitions. Okay, so we just define the GCD between 2 divisors. You just take the minimum of the valuations, A and B. And the least multiple, divisor. I don't. Okay, LMD. Huh? Okay. Of A and B, you take just the maximum of both of them. Okay. And so, why to think about these non-special divisors of a small degree? Because you have this theorem from Bowick, Dalai, and Menaher that they give you theoretical way how you choose the divisors G and H in a way that you can find a pair of LCP codes, okay? Linear complementary codes. And what do you need? So you have to choose G and H. So this first part has nothing special, okay? This is just for the construction basic of the code. And you need that the degree of the GCD between them is G minus 1, but you also want that the GCD is non-special. So you want a divisor of degree G minus 1 non-special. And you also need that the LMD of G and H minus D is non-special. Okay? So if you are able to find this in our function field, they prove that the pair is going to be a linear complementary pair of AG codes. Okay? So if you want to construct pairs of codes, you need to find non-special divisors of degree G minus 1 in your function field. Yeah? And if you have a pair of complementary pair of AG codes, if you want to get an LCD codes, well, you need to be able to find that differential that makes that place that the dual of this code is going to be that one. Okay? So our first question is, does non-special divisors of a small degree exist? So this was actually answered by Ballet, Le Brigand, and the third author. They, yeah, sorry. So they proved that, well, if you have enough number of rational places, you have non-special divisors of degree G on your function field. And this divisor is going to have support on your on rational places. Okay? And they also prove in the paper that a non-special divisor of degree G minus 1 cannot be larger or equal than 0. It has to have a one negative guide there. And this is also something very, well, useful for us. They prove that if you know a non-special divisors of degree G, then you take any rational place out of the support of A, and you take it off, minus it, and you get a non-special divisors of degree G minus 1. So basically, yeah, you just need to know the non-special divisors of degree G. The other ones you get. So can we get them? Well, then we just go to another work from Moreno, Lopes, and Gretchen Matthews, that they worked on finding no special divisors of a small degree on Kummer extensions. Okay? And so they presented some families, and no. Yeah, I did the same thing. Okay. No, last one. Yeah, here we are. So they presented, this is one family. They have more families, but we use this one. I'll just write here to explain what we did from here. So you have your Kummer extension. Degree of f is r. Okay, so usually you have, so you look to the function field over fq. So your polynomial is separable, has degree r. So you have r points that are totally ramified. So this gives you q1, qr. So these are all rational places. And they also choose, you do m and r be coprime. So you have one extra point. That's totally ramified, the infinite. So if you look to their divisor here, that is non-special of degree G, what they did is, on the support, they don't use all the points. They use r minus 1 points. So you have two rational places free to take off and get your non-special divisors of degree G minus 1. Okay? So you can get two different non-special divisors of degree G minus 1, just to choose in P as being, one time you can choose as this one, the other time as this one. Okay? So how can you use all these things together to construct linear complementary pairs? Well, you fix two non-special divisors of degree G minus 1, like that. Okay? And then basically you try to solve a certain system of equations. Well, this is really a simple idea how to do things. But yeah, you need to find G and divisors G and H, okay, such that the GCD is A is no special degree G minus 1, LMD of G and H minus D is going to be the other one. You can add a function here because you do nothing, you still have same degree and you have the same dimension, okay? And well, this part is okay, the last part. So yeah, if we find, oh, there is a typo here, huge typo, but if we find the G and H, then this is gonna be a pair of, a linear complementary pair of AG codes. So this is what we have to do. So what we did first, well, this I just said, we made like a general constructions for Kummer extension and then applied for some curves. Okay. So for example, this is just like one theorem. You have like this. So we showed, yeah, if you choose G like this and H like this, you can prove that the GCD is going to be exactly something like that divisor from the Gretchen papers minus like this guy. Okay? And this is going to give you a pair of linear complementary pair of AG codes. We also did something, well, this choice of G and the H, of course, it's not unique. You have other choices, so we have other choices that also works. Okay? And for some of them, okay, yeah. So for some of them, we are able to get linear complementary dual codes, LCD codes. And for that, we went to maximal function fields. So as Montanucci said on Monday, like maximal curves are the best curves to construct AG codes. So we have a similar theorem using a maximal function field. It means that the number of rational places is q squared plus 1 plus 2 times g times q. Okay. And then, if you have a maximal Kummer extension, you can choose your divisor D as being the zero divisor of this function. Okay? And then, if you choose G like this, you can prove that actually this code is going to give you an LCD code. That's all. Just, yeah. So, okay. And, well, we applied this for some function fields, like a generalization of the Hermitian function field. And then we obtained, for this one, you just apply the theorem. You obtain the pairs of codes, for example, over F9 with these parameters. So if you look to the singleton defect, it's just 3. So, well, it's very close to MDS. Huh? To me, it sounds good. Okay. And we also, yeah, just a second construction. We did something for a curve that was covered by the Hermitian curve. And as in the talk from Monday, if you have a curve that's covered by a maximal curve, it's still maximal. So we know that this curve is maximal. And we could construct LCD codes with these parameters. And also, again, if you add the dimension plus minimum distance, yeah, okay, you are far away, but not that much also from that. Yeah? Okay. So I'm just going to split, I just jumped the second part. So this is just for people that knows, like you have this Flassmann-Vlado sync bound on sequence of codes, and it's important to obtain sequence of codes attaining the Flassmann-Vlado sync bound, okay? So, yeah, in a second work with Adler, actually, okay, I'll just, this last one. So, yeah, using the ideas from the first paper, we could use a tower of function field and provide explicit sequence of LCD and the linear complementary pairs of AG codes, such that the sequence of LCD codes, and when we look to the pairs of sequence, both pairs attain the Flassmann-Vlado sync bound. And usually people have proofs like exist sequences attaining the Salzman-Vlado zinc bound, but they don't show you the code. And we show the code. Like, okay? So yeah, so, okay. But yeah, this is the code, but. And okay, and so I'll let you a question, like if you could provide non-special divisors of a small degree in another family of curves, like Artin-Schreiers, or separated variables curves, could be nice. You could do this kind of things again. But you need to find these non-special divisors. Okay.
Thank you very much, Luciani. Are there questions or comments? I have one. I got a little bit confused. The work of Le Brigand ballet doesn't, I mean, they don't show the existence of, only under certain conditions.
Yeah, I mean, they are very explicit. I didn't put things here, but like if Q is larger than 3,
it has to have many points.
Yeah, they use the zeta function to compute the and then yeah, but it's more exists. They have another paper from now, 2025, and now this year their paper. So they show some divisors, but the second paper comes after the paper from Gretchen and Hiran, and then so they already have that examples of G-1. So yeah, there's something new.
Other questions or comments? If no, let's thank Luciane again. Thank you.
So this. Arrumando o cabelo aqui com cabelo com. Tá. É o contrário. Espera um pouquinho. É o contrário.
Direita passa, esquerda volta.
Direita vai para frente? Ah, sim.
Esquerda vai para trás.
Tá certo.
Esse aqui eu leio.
Beleza, vou tentar na. Ok. Tá bom. Pode. Bom, começando um pouquinho antes, né? Acho que está começando. Ah, pode.
Obrigado. So, moving on, it's my pleasure to present Lúcia Moura. She'll talk about new covariant arrays of strength 4 and Q symbols from three truncated Möbius planes in PG3Q. Thank you.
Thanks. Okay, so it's very nice to be here and speaking in this nice conference. Long title, I try to state the theorem in the title, so you see if you want to see. So this is joint work with my PhD student Keanu Chokri and my colleague and friend Brett Stevens. So the plan for today, I'll first describe. Okay, this goes on. Okay, I'll first describe what we want to build. We want to build some combinatorial objects, and we will use finite fields, and some finite geometry plays a role there. And the objects we want to build are covering arrays, so we'll define orthogonal arrays, covering arrays. Then we'll talk about another construction, more than 10 years old, that is for covering arrays of strength 3 that we had in the past. And the result today is a generalization that for strength 4. And that's this third part. So let's start. Okay, there's a delay, right? Okay, so what's an orthogonal array? An orthogonal array has n rows, k columns, symbol set V. And the important property is that you have a certain strength T. So that T will tell me I should pick any T columns of that array, look at that subarray, and every T tuple of the alphabet should appear the same number of times, lambda. Okay. Many cases, our lambda is going to be 1. So an orthogonal array with lambda 1, some of you might know as an MDS code. The rows are MDS code, and the relation is that k minus t plus 1 is the minimum distance. Okay, but the lambda could be larger. You can define this as a combinatorial object, doesn't have to necessarily be linear, right? So it's, in this case it is, but it doesn't need to be. Okay, so that's an orthogonal array, classical object, and I have been studying a lot covering arrays. See, small difference in the definition, everything is the same, except that instead of exactly lambda times, you say at least lambda times. So it's a covering problem. So I get that orthogonal array, it is a covering array because everything appears exactly lambda times, so it also appears at least lambda times. But the interesting case is when you have many more columns, you want to build something, many more columns for which we don't have an orthogonal array. So we will have to have more rows. You don't care, you don't mind about repetitions of the T tuples, but you must have those. I will show you, this is not a typical example, right? In the orthogonal arrays, my n number of rows has to be then exactly the number of repetitions you need, which is a constant lambda v to the t, or if lambda is 1, is v to the t. But for the covering array, you may have more, right? You need at least those, but you may have more rows. For example, I'll give another example here in which I have, now it's binary alphabet strength 3. So I should pick any 3 columns and I should see every T tuple of the alphabet appearing at least once. But there may be repeats. All the 8 tuples appears and some of the triples, for example, appear more than once. And the objective is to minimize the number of rows. And there are tables of best covering arrays for given, T, K, V. What is the minimum n that you can achieve? And what we're talking today is about a construction in which you try to get, for certain parameters, we get the n much better than known bounds. And we use finite fields, so it's a good opportunity to talk here. Okay, so we are going to be using linear feedback shift register sequences over finite fields. And there is a paper in '98 by Munemasa where he looked at some arrays built with those sequences. And he observed, in those cases they're only binary, okay? But in those cases they observed that there are some arrays built from these sequences that they have strength 2 and almost 3. And we're gonna use things like this to build covering arrays. Actually, so what it means almost a strength 3. For example, in this case, I have all the pairs covered twice, but the triples are covered for some columns, but not for others. So out of the 35 triples of columns that I need covered for, 28 are okay, but 7 are not. And they are listed there, which triples of columns do not have the coverage achieved. Has to do with geometry, but we'll get to that later. So in this earlier result, more than 10 years ago, with Sebastian Rapphurst was my student, and Brett again, we constructed covering arrays of strength 3 using 2 of those almost strength 3 things. And together, they form a covering array of strength 3. Because, triples that fail, of columns that fail on the top part of the array do not fail at the bottom. And these have some connections with geometry that I will talk later. And then this gave this, I can actually look here. Nice. This gave these arrays, right, to these parameters for every q prime power. And the geometrical property, what we actually have is we have a, things fail on the top array on points that are in the same line in a projective plane of order q. But then you have two projective planes of order q in which triples that are in one projective plane are not in the other. So if it fails in one, it doesn't fail in the other. So there was that geometrical connection. Okay, so now what happens? We for a while we have been looking about doing similar things for strength 4. Now getting a polynomial of degree 4, etc., be in this space of dimension 4 and do similar things, pasting two things that are almost away of strength 3, but now can together might give strength 4. Okay, this in this paper that has many other things, we did some computational searches, and we actually found, just for the case k equal to 4, that I could stick two of them and taking specific points, and these points corresponds to what's an ovoid. Okay, but this was only worked for this particular sporadic case, and since then we didn't know anything else to do. And then more recently, we proved the theorem that I'm presenting today, which is for every odd prime power, I would take what are the points of an ovoid, but I take only half of them. Then I can show very specific pieces of this ovoid that are in 3 parts, not 2. I have 3 parts, and together, each of them are an orthogonal array of strength 3, almost 4, and the 3 together form this covering array of strength 4. So that's the result I'm talking today. Only works for q prime power. Q odd prime power, not the even ones. And it's not the full ovoid, it's half of ovoid. And this is what I'm going to talk in more detail now. Okay, let's see. Oh, already 8 minutes. I'll go fast on this, but I want to explain a little bit how the original construction works so I can talk about the generalization. So we started looking at this by, following the ideas of Munemasa and constructing the sequences using linear feedback shift register sequences. We start with a primitive polynomial. Then there is an alpha, that's the root of this polynomial as a primitive element, and then you generate a sequence out of it. So the polynomial is the characteristic polynomial of this linear sequence. We need to pick 3 initial, m initial values, right? The polynomial has degree m initial values, construct the sequence in this way, and if the polynomial is primitive, this sequence has a maximum period, which is q to the m minus 1. Very interesting properties for this that allows us to build the arrays we need. So this is an example for M3 and Q also 3. So when the sequence has maximum period, it's called an M sequence. So we'll be using these M sequences. Not a lot of time to talk about all these properties that we need, but one of them is that every window of size m that I go over the sequence, I can see all the tuples of the alphabet that are non-zero, exactly once. Also, if I pick slices, so I have my period q to the m minus 1, but if I pick slices divided by q minus 1, then the consecutive slices are multiple of each other. In this case, I have 2 slices, q minus 1. So I have these numbers, and then I have this times 1, and the same numbers times 2. The two tuple balance property will tell me that guys at the same distance, if I look at all the pairs at the same distance in the sequence, all those pairs occurs the same number of times for the non-zero ones, exactly q to the m minus 2. One less for the 0, but we'll fix it by adding an extra row of zeros. And also the sequence can be built simply by taking the trace of that primitive to the power I will generate a 0, a1, just with this, using the trace, right? So I won't go through this. Basically, what I'll do is I will get the length is exactly one of those slices of dividing by q minus 1, right? Q to the m minus 1 divided by q minus 1. And I will get all the slices of that size and put it in an array. Okay, that's the array build plus the row of zeros. And that's what Monema's already observed. This is an orthogonal array of strength 2 with an index high, right? Q to the m minus 1, right? Those pairs occurs the same number of times, but many, right? Not only lambda 1. And this is what we use. So here is the sequence. The period of the sequence is in red, but now I take a slice of size q minus 1, dividing by q minus 1, and that's the array, and I stick a row of zeros. So these are all the shifts of the sequence, q to the, this case, q to the m such elements, right? I'm using for m equals to 3 to build the array of strength 3. So this is an array of strength 3 almost, strength 2 almost 3. The almost means that the places where it fails are on columns that corresponds to points in a projective plane of order q. Exactly. And then that construction with Raphurst was to find then another one, right? Another array. So here is the first array. The other array will be a different sequence with a different primitive. The primitive will be alpha to the minus 1 instead of alpha. Generate the same sequence. And, right, this is a big array like this. It can be generated by just the first 3 rows, linear combinations of the first 3 rows, so a compact way. This first part has to do with alpha, all the powers of alpha are these vectors here, and at the bottom, all the powers of alpha to the minus 1. And it works. Those are whenever I have, whenever something fails for the top, it doesn't fail for the bottom. So 2 projective planes so that the one line in one intersects in a line on the other at most 2 points. And then we got this, right? 10 years later, this is still, for those TK lambdas, is still the best bound for k different than 2 and 3 in these tables. And there is this nice paper that interpreted this as you know, this result is, they call projective planes such that one line in one intersects a line in the other at most 2 points, orthogonal. So what we have here is a pair of orthogonal projective planes do the job for strength 3. And now we want to describe what we did for strength 4. Okay, so I have 6 minutes. Okay. Okay, so let's go back to what we have for 3, right? These are the points we have for 3. So we use the whole, the columns of my array are points, correspond to points of the projective plane PG to Q. I have exactly Q cube minus 1 divided by Q minus 1 columns. Then I build 2 arrays, interval arrays, from 2 primitive elements. They're polynomials, right? Alpha and alpha to the minus 1. Alpha to the I is what's in column I, etc. Right? Then each array is a 2-away, that's almost a 3-away, and the missing triples are 3 collinear points on a projective plane of order 2. But then I have the 2 arrays together, they are 2 projective planes, so that 3 points that are collinear in one are not collinear in the other. And that did the job for strength 3. So what we did for strength 4 is you use, we have Q is an odd prime power, okay? Then I will take an ovoid, which is a set of points, 3 such that no 3 of which are collinear. But I don't pick, it doesn't work to use the whole ovoid. We use part of it, half. I will show you how we pick them. And then I'll pick 3 subinterval arrays, one using the ovoid. If I pick just alpha to the q plus 1 and every index I here, I get the ovoid. I get an ovoid in PG3Q. And then I get those for the first. And then for the second, I use alpha 2 q plus 1. And for the third, alpha 4 q plus 1. Very simple construction. Okay, very simple to describe. But I don't use the full ovoid. I just use q squared plus 1 over 2. Each array is a three-way. That's almost a four-way. Where it fails, the missing quadruples that fail are 4 coplanar points in the ovoid. So what we have to show is that if something is coplanar in two of the 4 points, where I miss the 4-tuple coverage, coplanar in this ovoid, it's not on the third. Okay? Or in other words, the intersection of, well, we'll get there, because I need to talk about a few more things. So, I'm taking here an ovoid for q equals to 7. I'm taking an ovoid in PG3Q. There are 50 points, right? Q squared plus 1. 50 points in this ovoid, which are this, represented by these vectors of dimension 4 here. Here is some rows of the array, which are linear combination of this. Okay, but I'm concentrated on this part, right? What happens? Whenever I have zeros here, this will correspond to planes intersecting the ovoid. So they may intersect in a circle, or they may intersect in a single point. For example, in here, intersecting a single point, I have no problem. This will not cause any problem with my coverage. But when it intersects in q plus 1 points, in many cases, like this, intersects in q plus 1 points, any 4 columns that are in the same plane, right? I can see because of those 4 zeros, I know these 4 points are in the same plane, I have a problem. So in this, this q plus 1 points has several sets of 4 points that give me a problem, right? So I will have this one, and then that's my full ovoid, I throw away half of it, and then I'll get, before I get alpha, now I get alpha to the q plus 1, now alpha to the 2q plus 1. So position 0, position 2, 4 of this array, I will copy at the bottom. And then position 0, 4, 8, etc., copy at the bottom, right? Throw away the rest. These are the 3 pieces. And for each of these part ovoids, right, the plane sections that are not those single zeros, but the ones that have q plus 1, right, intersect this ovoid, form a tree design with these parameters, and that's called a Mobius plane. Okay, so the problematic points are together in blocks of this Mobius plane. But, right, so I cannot have more. I may have 4 points on this, but I don't want to have the same 4 points in another ovoid and in the third ovoid. That would be a problem. But in this case, it just doesn't happen. So the truncated, we invented this term. Truncated Mobius plane is part of half of the Mobius plane. Now another permutation of the same points is from another one, and this is another one, another part of a Mobius plane, right? And this together, what we show is that the intersection of these circles, the plane sections of each Mobius plane, the intersection of one from each, the intersection of the 3 cannot be 4. They are at most 3. And then this means that this together gives a covering array of strength 4. And those are the parameters, right? Number of columns is half of the size of the ovoid. There are 3 of them, but I can throw 2 rows of zeros are not needed. I can reduce that. And then this decreases the bound on the best known covering array. These are the number of rows on the covering arrays in the tables by Coburn. And then we reduced for every q greater than 11, odd, right? Odd prime power. And as Q grows, it's getting about 25% reduction on the size of the number of rows in those. That's it. And final slide. If my polynomial has degree 2, I can retrieve Bush construction for an MDS code, same parameters at least. For strange 3, I have an OA that has a strange 2 and almost 3. I paste 2 of them. That's Raphorst construction. For 4, for Q even only the case 4, we were able to paste 2 copies of I strength 4 there and obtain almost 3 strength 4 and obtain it. But the current paper that's more general is for all odd prime power. We didn't use the whole size of an ovoid, but half of it. But with 3 copies, we do that. So the question is, what's next for 5, right? Well, how this would generalize for 5? Maybe some of you that know more geometry than me may have ideas. And what to do with the even case. Because these are the main questions, right? Q even, we don't have anything like this yet. And then higher strength would be interesting. And thank you.
Thank you very much, Professor Moura. Lucia, are there any questions or comments?
Some references.
I have kind of a strange question. You're talking about projective planes and ovoids and such, and these depend on being classical, it seems.
Really?
Classical? Like the Sarkisian plane, for example? Yes or no? Or?
Yes. We are using the finite field.
So you think there would not be like a geometric way of... if I give you a projective plane which is not classical, there would not be like a geometric way to executing this. Or...
We didn't think about it because we know.
Yeah, because we still don't know if there might be projective planes of non-prime power orders, for example, right?
That's
so
true.
this
That's
might,
true.
pose new questions, right?
That's true. Yes. And then you'd have to have one, and then have 2 with this stronger property, right? No. The construction is with finite fields is using this vector space.
Okay, thanks.
More questions or comments? So if not, let's thank Lucia again.
Thank you. Coffee break.
So, good afternoon. Moving on with the session. It's my pleasure to present Luis Finotti. He'll talk about minimal degree liftings and error correcting codes. Thank you, Luis.
Thank you very much. I appreciate the opportunity to speak here. So thank you to all the organizers. Thank you for coming. If you're hoping for something different, I guess careful with what you wish, but hopefully you'll find this somewhat interesting. As a disclaimer, if you're mostly interested in the error correcting codes part, maybe you still have time to run to the other talk. My main use of the error correcting codes is for motivation. I'll give you some examples of the applications of the theory, but my personal interest is the questions that were raised by these codes. So let's get started. So I have to introduce these objects called bit vectors. I'll do it very briefly with motivation coming from q-adic integers. So imagine that you have some q equal to some power of a prime p, and you have an unramified extension of degree r. So we can create then the q-adic integers, which I'll denote just by z sub q. This is a familiar object in number theory. But one thing that you can do, I think I went a bit too far here, is represent, the usual way to represent elements in ZQ is to choose some set of representatives for the coefficients in here, which is a complete set of representatives for the residue field. So if you are in FQ, for instance, a good choice would be the Q minus first roots of unity, and 0, right? So then all your elements of ZQ are power series in P with coefficients as these roots of unity with 0. Now, what you can do if you want to, for instance, put in this in the computer, you can just collect the data. So you can collect only the coefficients in there, right? So you convert these infinite series to an infinite sequence. But since these coefficients are uniquely determined by the reduction modulo P, might as well reduce them all modulo P and have simpler objects. So in this particular case, these reductions in here are in FQ, a much simpler object than elements in ZQ. And for reasons that I'll explain in a second, what we usually do is take powers of these coordinates. So pth for the second, pth squared for the third, and so on. Okay, so this gives a way to visualize these elements of ZQ in a different way. And here we have a map, a natural map from FQ to the set of representatives that we chose, right? So here are just the Q minus first roots of unity in ZQ together with 0. And we call this map, therefore, in this context in here, which takes just an element of FQ to this vector in here, start with the same element in FQ and zeros everywhere else as the Tachy-Miller lift. Now, what we can do at this point is ask, well, this is more than just elements sitting around you is a ring. So we have a sum and a product. And how do you translate the sum and product of power series to these vectors in here? Right, so we know how to do it with the power series. We carry basically to the next power of P. But how do we do it with these vectors? How do you translate the ring structure? Oops, wrong button. Sorry. That went very far. Yeah, so how do you translate? Well, what happens is that there are polynomial functions that give you the result of sums and products. So this is how to represent the sum and product of q-adics in terms of these vectors. And these polynomial functions that give you the coordinates of the sum and the product they have, well, integer coefficients and depend only on the characteristic. They do not depend on Q, they depend only on P, okay? So what you can do at this point is say, well, what if I don't start with a finite field in characteristic P, but any field in characteristic P? You can still use exactly the same formulas here as the S sub i's and the P sub i's, to define a sum and a product, and what you get is indeed still a ring. And this is the ring of its vectors. Okay? So it's a different way in this construction is a different way of seeing just these q-adic integers. But again, the point is that now you can generalize to any field of characteristic P, and if your field is perfect, then you get a nice ring that is what's called a strict P ring, which I'll say what it means in a little bit. Okay? But if you want to, you can think of these Vit vectors just a way to see q-adic integers in terms of vectors instead of in terms of power series. So one thing that you have to keep in mind throughout this talk, because we're going to talk about a lot of computations, and one thing that you have to keep in mind is that computations are very difficult. For instance, if you want to look at the next S2 here, for p equals to 31, you get almost 153,000 monomials for that formula. So computations with Vit vectors are very difficult. All right, so, and similar to before, so we still have this so-called Teichmüller lift, which is exactly the same as we had for finite fields, just now for any perfect field. And this, when restricted to the multiplicative groups, you get an injective group homomorphism. Now, what we can, so here is just very briefly a few properties of these rings of Vit vectors. So we start with a perfect field. So this guarantees that you have nicer properties. Using the same formulas for sums and products that we've seen in the previous slides, we get a commutative ring, which is actually a domain. Characteristic is 0. 0 is represented by the 0 has zeros in every entry. 1 has 1 in the first entry, has zeros everywhere else. And if you multiply a vector by p, well, in terms of your power series, you're just shifting the power series, but because of those powers that we introduce in the vectors, you also have, oops, again, pressing the wrong button. I apologize. So you get these powers in here. And so in particular, mixing these two, you can see what happens with powers of the prime p in the Vit vectors. And the units are just vectors where the first entry is a unit. And here is what it means to be a strict P ring, this nice property that these Vit vectors have. So this is a local ring with maximal ideal generated by P. The residue field is exactly the field that you started with, so this perfect field. You have this filtration by the powers of the ideal generated by P. This gives you a metric, and the ring is complete with that metric. You know, it's exactly the same properties that you have in your q-adic integers. And just like truncating the power series, you can truncate their Vit vectors, and they correspond exactly to reducing modulo a power of P. Okay, so like as usual with the q-adics, you know, you're going to deal with approximations. The approximations is just truncating. And here we have again the Teichmüller lift, and of course this was our motivating example. If you just use a finite field as your entries, you get the q-adic integers. All right. So one interesting property that these also have is that you have a lifting of the Frobenius. So whenever you're in characteristic P, you have the natural pth power Frobenius. And by raising every single entry of a Vit vector, which is in characteristic 0, right? If you raise every entry of this Vit vector to the pth power, what you get is a commutative diagram in here where pi is this reduction modulo P, which is just looking at the first coordinate. Okay, so we have this mapping here, which is a lifting of the Frobenius. And not only that, the Teichmüller lift gives you a section in here, which also makes this diagram commute. Okay, so again, in the bottom here, we're in characteristic P. On the top, we're in characteristic 0, and we have this lifting of the Frobenius. Now, can we do something similar for curves? And what do I mean by that? So again, you start with a curve over your perfect field in characteristic P. and we have the natural Frobenius in characteristic P. So the question is, can I find a curve over the ring of Witt vectors that reduces to my original one? Now, in here, you're applying the Frobenius in characteristic P to the coefficients of the equations defining your curve. Well, you have a Frobenius for Witt vectors. You can also apply in here, and it's also going to reduce the corresponding curve. So the question is, can I find this curve in here for which I can find a lifting of the Frobenius? So I have a morphism of curves on top in characteristic 0 that makes this diagram commute. And you might ask, well, maybe, can I also have something like the tachymeter lift, something that goes up, some lift of points? Now, the answer is, well, due to Dorian and then extended by Serre and Tate, is that you can only do that for ordinary elliptic curves. So the curve has to be of genus 1 and ordinary. Otherwise, the answer is no. So here's the picture. And not only that, there's only one curve on top here up to isomorphism for which this lifting of the Frobenius exists. And this is the so-called canonical lifting. Okay? So there's a unique, given an ordinary elliptic curve, there's a unique elliptic curve over the ring of Witt vectors for which this happens. Now, the nice thing is, of course, our elliptic curves are groups. And as before, you might want a group homomorphism that goes up. And that also does exist, is the so-called elliptic tachymeter lift, which is going to basically take points of your curve in characteristic P to points of your lift. Okay? So this comes with the canonical lifting. So associated to canonical lifting, you have this elliptic tachymeter lift. So we have an analog of the diagram we had before for multiplicative groups. Now, there's lots of applications. Of course, coding theory is the main focus in here, but there are applications to point counting and finding rational points also. So this is a very interesting subject. Now, again, the main focus in here, the motivation for a lot of what we're going to do is application error correcting codes. So Volek and Walker use the canonical liftings, the elliptic tachymeter lift, to construct error correcting codes. I'll say a few words about that, hopefully, at some point. And the key facts are the degrees that appear in this elliptic tachymeter lift, which I'll also say a few words in a second. But here's a theorem. So let's assume p equals greater than or equal to 5 for simplicity. So here is your tachymeter lift. So again, you take a point in your curves. You can see here a curve in characteristic P and lift to a point over the ring of Witt vectors. So a point x0, y0 is mapped to a pair of Witt vectors. Now we can ask about what are these coordinate functions in here for the Witt vectors of x and y on the lifting. It so happens that these are polynomial functions. So these fi here are polynomials on x0. And these functions in here are polynomials of the form y0 times a polynomial in x0. And what is important, and the thing that we have to remember, I'll say a lot of things, but some things that we do have to remember is that we care about the degrees of these polynomials because they affect the resulting codes. So what we want is to have small degree polynomials for these liftings of points. And that, for that, we were able to compute upper bounds for these degrees. It's almost always equal. We know exactly when we don't have equality. By the way, this theorem was proved by Volek and Walker for I equals to 1. And then in my thesis, many years ago, I generalized it. But we have upper bounds. Don't worry about it's not going to be in the final. So we don't have to worry about these degrees. So what we care about is the size of the degrees. And we also have a formula for the derivatives, which allows us to develop an algorithm to actually compute this canonical lifting and the tachymeter lift. Okay? Now, the thing is, for I equals to 1, so you're looking only on 2 coordinates, what happens is that the degrees for these two polynomials, F1 and G1, are as small as possible when you're talking about the canonical lifting. So imagine that you start here downstairs with an elliptic curve. If it's not ordinary, and so there's no canonical lifting, the degrees are going to be high. If it is ordinary, and you don't use the canonical lifting, the degrees are going to be high. So the best that you can do is to start with an ordinary elliptic curve and the canonical lifting and use the tachymeter lift, and you have the smallest possible degrees, which yield the best estimates for the parameters of the codes. So, so that was perfect for what Volok and Walker did. They only look at the first two coordinates, and I looked at this third coordinate, and I found out that that is not the case anymore. The tachymeter lift does not give you the best degrees. They're not the smallest degrees anymore. And since we're interested in constructing codes, that's not ideal. So I started to look at how we can minimize these degrees, and the same techniques could be applied to hyperelliptic curves. So I worked on generalizing to hyperelliptic curves. So these allowed me to, made me introduce two notions: minimal degree liftings and absolute minimal degree liftings. The minimal is just we start with two curves, the one in characteristic 0 and the one the reduction modulo p, and given the two, how do you get the minimal degree? The absolute, you only start with the one in the bottom, and you search among all the liftings of it, which one is going to give you the minimal degree. In any case, here are some results about these minimal degrees. So if you start now with a hyperelliptic curve, with the polynomial degree d on the right, one can find upper and lower bounds for the degrees that you can get. So these are actually sharp. So in practice, if you start with any curve in characteristic 0 and reduce it, you're probably going to get the upper bound. But we also have a lower bound, which is what we want to achieve. So we're going to find curves for which we can achieve this lower bound, because these would yield the best codes. And we have conditions that are necessary to achieve this lower bound. The first is that this coefficient of x0 to the p minus 1 to this polynomial on the right of your hyperelliptic curve raised to p minus 1 over 2 has to be non-zero. For elliptic curves, that's exactly the Hasse invariant. So that has to be non-zero if you are able to achieve the lowest possible degrees. Not only that, in characteristic p, not every polynomial is a derivative, and it's necessary that this expression here, again, f is this polynomial in your hyperelliptic curve, this expression must be a derivative. And that, and furthermore, these polynomials which are recursively defined, so this is the case where I equals to 1 in this expression in here. But you can define, so this is a derivative, so-called the integral f1, and these expressions on the right here, I would have to all be derivatives. So we have, don't worry too much about what these conditions are, but I'll mention these conditions in a little bit. Now, so if you start with an ordinary elliptic curve, that's an interesting case, because what happens again, Volok and Walker already dealt with case I equals to 1. That's elliptic curve and tachymeter is the best. As I mentioned before, we can get better bounds than the tachymeter for I equals to 2. So I'm starting with only the curve in the bottom here and trying to find the best one on top and the best map. Up to the second coordinate, tachymeter, lift, and canonical lifting. Whenever you go to the third coordinate in here, F2 and G2, it's not the tachymeter anymore, as I mentioned, but the curve on top has to be the canonical lifting. So the curve is still the canonical lifting, even though the map is not the expected one. And in fact, so you can get that case. I had a conjecture that Tate proved. I had reduced this case to a conjecture on just cubics over finite fields, which Tate proved. So I can get this lower bound for I equals to 2. Now, the funny thing, I was expecting that if you go now for I equals to 3, so the fourth coordinate, that something similar would not happen, that still you had the canonical lifting, but some other lifting of point that's not the tachymeter. But that's not true anymore. The curve on top in here does not have to be the canonical lifting anymore. So that was surprising. But still, the computations are difficult, but I could compute for the fourth coordinate and p less than or equal to 11 and always be able to get the lower bound. Now, genus greater than or equal to 2 is more complicated. I'm going to skip these because I'm almost out of time. So I just want to mention a few less results in here. The g equals to greater than or equal to 2 is more complicated. So finding a necessary condition is weird. So we looked at lots of examples. We did lots of computations and tried to find when we're able to get these minimal degrees. And here is a strange result. So for only genus 2, so this very specific case, what happens varies considerably in terms of your priming there. So for p equals to 7, it suffices, it seems, that your curve is ordinary in the sense of the Jacobian of this curve is ordinary. But there are lots of examples, like for p equals to 5, you still need the hyperelliptic curve to be ordinary. But there's an extra condition. This extra condition here, this has to be, well, in the case that you want to have the minimal degrees, this has to be equal to 0. And these conditions appear, and it's sporadic. Some cases only being ordinary is enough. Sometimes you have these conditions that show up, and we can't find what they are. So I guess I'll have to stop here. Sorry for going a bit over.
Thank you very much, Luis. Are there any questions or comments? Okay, if not, so let's thank again, Luis. Thank you very much.
Hello.
So it's a pleasure to present the last speaker of the session today. Is John Schicke. He'll talk about additive and multiplicative complexity of finite fields and semifields. Thank you, John.
Thanks very much. And firstly, thanks to the organizers for this great opportunity to visit this beautiful country for the first time, hopefully not the last time, if they'll let me back. So I'm going to talk about some joint work with Jean-Guillaume, who's based in Grenoble, and Stefano, who is from Italy, but is currently based in Sweden. So I'm talking about finite fields, which I guess everybody here knows a lot about, and finite semifields, which may be less well known. I'm going to start with a theorem, which is that finite fields are interesting. I guess I don't need to convince you guys of this. We have a quick proof of that, the fact that we're all here. So I think this is straightforward. But often when you're trying to do things using finite fields, sometimes you don't actually need all of the axioms in order to achieve what you're trying to do. So for example, constructing a projective plane, you don't actually need associativity of multiplication. So if you don't need it, why not throw it away? So a finite semifield is basically just a finite division algebra where multiplication is not assumed to be commutative or associative. Excuse me. So these have a long history. The first example in the infinite case goes back to the 1800s. Graves, who was Irish, constructed the octonions, building on work of more well-known work of Hamilton, who was also Irish. That's the end of my flags. I just wanted an excuse to point out that Graves is Irish. And then so in the finite case, Dixon in the early 1900s constructed the first proper finite semifields. So second theorem is that finite semifields are also very interesting and important. And the proof of this, well, so my daughter, who's at home, will be watching this tomorrow, knows sometimes when you ask why, the answer is just because I said so. So for the purposes of today, you can just take my word for it that they're interesting. But if you want to know why, I'll happily spend hours telling you. What I'm interested in for the purpose of this talk is the problem of efficiently performing multiplication in either a finite field extension or a semi-field extension, or more generally just an algebra. This is not really my area of expertise, so I apologize for any lies I tell you. So we would like to be able to perform a multiplication in algebra as efficiently as possible. But what that means maybe depends on who you're talking to and what your goals are. Well, to start very generally, well, if I want to describe an algebra, which again, not necessarily associative, I can say take my two of my standard basis vectors and form their product in this way, expand it in terms of the same basis, and you get these structure constants Ti, J, K. And so, for example, to form a product of two vectors A and B, we could try to do it in this way. So we've got a bunch of products of these kind of coefficients or coordinates of the vectors, and then these structure constants out the front. So you might say, well, we've got maybe n squared products of these things, and then certain number of additions to do. Just to give you an idea of what these structure constants could look like, and to give you your first example of a semifield in 1 second. So matrix multiplication, from which this type of study is, let's say, most well known. You get these guys. If I take the field extension f2 to the 4 in the same space, you get this guy. And then there's two other semifields of the same order, 2 to the 4. And this is what these look like. Again, take them home and play with them if you want. We won't do anything apart from acknowledge that they exist for now. Okay. So how do you figure out, well, what's the best way or the smartest or the quickest way to perform a multiplication in this algebra? So it depends, again, on the context, what actually you would care about counting. So you could care about multiplying these coordinates, AI and BJ, and you might care about adding and subtracting, or possibly scalar multiplying products of these things as well. So, okay, the standard naive way of doing 2 by 2 matrix multiplication, we know we have 8 multiplications and 8 additions. And And the very famous Strasson's algorithm tells us actually that you can do it in fewer multiplications, just 7. I think Daniel told me that this paper was only like 2 pages long or so. We just said, bam, here it is, and walked away, which is pretty cool. And then Winograd showed that actually you can't do any better than 7. So that's obviously hugely important and plays a role in lots and lots of things. One thing that's worth noting is that you're saving yourself a multiplication, but you're actually trading that in for a lot more additions. So in the case of Strasson's original algorithm, I think there was 18 maybe, and Winograd improved it a bit to 15. So why is that better? Well, basically because in the matrix multiplication world, you're applying this recursively. So if you have a big matrix, you split it up into blocks, and then you split those blocks and split those blocks and so on, and do it recursively. And very roughly speaking, this is where I lie to you and hide loads of stuff I don't understand under the carpet. Basically, the number of multiplications shows up in the exponent, and the number of additions shows up in the constant. So it's kind of the multiplications are much more important to count. So that's why it's fine to throw in loads more additions, even if you're because you can get to save yourself a multiplication. So kind of, again, another lie, but roughly speaking, if we're doing something that have some sort of recursive implementation, then I say only multiplications matter. Multiplications matter a lot more. But if you're talking about a fixed algebra with a fixed size, then actually both these additions and multiplications are equally important to count. So what's the goal here is to basically try to study some division algebras, semi-fields and fields of a fixed size, and try to find the lowest possible algebraic complexity. That just means lowest possible number of additions and multiplications to perform it. And my goal, because I think semi-fields are better than fields, is to show that there exists some semi-fields with lower complexity than a field of the same size. So just to spoil a little bit for later on, I had previous work with Michel Lavrau showed that there are semi-fields that have lower multiplicative complexity than fields of the same size. So this work was then bringing the additions into the play as well. So how do we go about this? How do we save multiplications? How do we kind of study these problems? So first start with multiplications and do additions after. So one good idea is to break up your multiplication into a bunch of linear forms. So let's say these LS are vectors or linear forms, if you wish. Form these dot products, and then only do so basically I'm doing some additions and scalar multiplications in here, and then multiplying the answers by each other, and then multiplying them by some other vectors at the end. So, and this number t at the top is, if that's low enough, then that's going to save us some operations, and we can then just do t multiplications. This is effectively working as with those tijk things, viewing them as a tensor and looking for a tensor decomposition. Okay, so looking for rank 1 tensors that sum up to the cubical array, if you wish. Okay, so again, this is all well known and very well studied and important stuff. And this number, smallest possible number t, is the tensor rank. So basically, how many multiplications do I need is the same as saying, can I calculate the rank of this tensor? And calculating the rank of a tensor is an extremely difficult problem in general. It's one of these NP something somethings problems. Okay, so just to introduce a couple of things I'll use later on. When I have this tensor decomposition into these L, or, and P guys, I'll just pack them together into matrices to be able to study them a little bit more easily. So I just have my vector is going to have length n, and then I'm going to have t columns. So I'm going to have a t by n, n by t matrix, sorry. Usually these are transposed, but I just wanted to fit them on the slide better. So, right. And I can write the tensor is then t of L or P. Okay, so if I can find these matrices, then that saves ourselves some multiplications. And yeah, these things are not unique. There's lots of different triples that can give you the same tensor. So just a very simple, small example for doing the multiplication in Fq². Well, basically, it's all just some tricks for multiplying polynomials. We want to form this product here. We break it up in different ways, do some additions here. So these are linear forms, A0 plus A1 and B0 plus B1. And then by doing clever choices, we can see that we actually only need 3 multiplications. So then those L and R matrices are just the linear forms here. So that's A0, so that's the column 1, 0. A0 plus A1 is the 1, 1, and the A1 is the 0, 1, etc. And then the P matrices is those other guys stacked into columns. Okay. So I've remarked at the end here that then actually finding the number of additions, once I have this kind of best possible multiplications, finding the number of additions is not straightforward at all, and it really depends on these choices of L or P. So I'll come back to that a bit later. So that's if we wanted to save on multiplications, we need to study the tensor rank. If we want to save on additions, well, basically it boils down to a problem of the complexity of performing a vector matrix multiplication. So basically, I want to find all these linear forms, or I want to multiply my vector A as a row times my matrix L. And this is something that's been studied a lot in its own right, usually with respect to upper bounds and so on. So I'll just give an example to see what actually this thing works. So for example, if I have a tensor decomposition of a particular guy, and I end up with this as my L matrix, and I want to form all the linear forms by, say I want to find A0, A1, A2, A3, A0 plus A1 plus A2, etc. And I want to do it in as few additions as possible. The idea is basically to throw in extra columns if necessary, so that what you end up with is a matrix where every column is a sum or a difference of 2 previous columns. So I've added these 2 guys in blue, and now if we check, we can see that all of these things are just additions or subtractions of the previous guys. So if I want to calculate the last column, 0, 1, 1, 1, so A1 plus A2 plus A3, it says, well, I can first add A2 plus A3 and then add on A1. But basically, having done the A2 plus A3, oops, there we go. It's all bound to happen sooner or later. Slow down. One more. There we go. So that means that we can do this using 6 additions. And something that's worth noting, that here's a 4 by 9 matrix where we maybe think we've got 1 extra linear form to calculate, so it should take more additions, but actually that's not the case. This one, that's already in the form where every column is a sum of 2 previous columns. So we'll see later that what this kind of tells us is that optimizing our multiplication doesn't necessarily optimize our overall complexity. I'll come back to that later on. But basically, we can put all these things together to say that, well, if I have a tensor or a multiplication in algebra, and I have these tensor decomposition with these L or P matrices, then the total number of operations I need is 2 times the multiplicative complexity, plus the sum of these linear complexities, and then minus an n. Okay, so I'll hide some things under the carpet. Basically, it's kind of this, it's a good idea to optimize both, but not necessarily, it's not necessarily true that having your smallest possible multiplicative complexity gives you the best overall. Okay, so that's what I said there. So let's just jump to some results. So the kind of known bounds go, well, firstly, we can now focus in on the case of fields and semifields. So if we have a tensor decomposition of a field or a semifield, these L or P matrices are all generator matrices for linear codes with a minimum distance at least n. Okay, so it's not too difficult to show that. So at least we could say, well, our question is not just about random LRPs, but LRPs that are coming from good linear codes. In turn, this gives us a bound that my tensor rank or my multiplicative complexity is at least the length of the shortest code with dimension n and minimum distance at least n. So again, our singleton bound gives us 2n minus 1, and that's possible if and only if q is large enough. So for small q, then these kind of bounds become much more interesting. What about upper bounds? Well, for the finite field, there's the famous Chodnovsky squared algorithm using fancy algebraic curve stuff that everybody in the audience knows more about than I do. And there's lots of other work in recent years, various authors to kind of use some algebraic curves to get the best possible known implementation of finite field multiplication. So here's a table just for the field extension fq to the n. The lower bounds are coming from the coding theory. The upper bounds are coming from the algebraic curve stuff. And these red ones is where there's gaps. So where there's maybe potentially better algorithms than currently is best known. There's one here in the case 3 to the 5, which I'll give some results on in a second, where there's a kind of computer example from which doesn't come from the algebraic curves. So there's a nice question I can pose about that in a minute. So then bringing in semifields into the picture with Michel, we showed that there were semifields of order 3 to the 4 with lower bilinear multiplicative complexity than the corresponding field. So because semifields are better, everybody knows, you all agree by now. So with Jean-Guillaume and Stefano, one of our contributions so far has been to take some of these algorithms that were developed for finite fields and adapt them to semifields. And in particular, I think I'll just skip to the table, maybe not. Yeah, so basically we found that there's two semifields of order 3 to the 5 with tensor rank smaller than the field, or at least the currently best known version for the field. And by a little bit of coding theory tricks, I'm running short on time, so I'm not going to spend time on it, but we were able to show with some, say, clever theory to reduce a computation to show that the tensor rank of the field of order 3 to the 5 is 11, and that there are semifields of order 1 smaller. There's also some semifields that might have tensor rank 1 bigger, which is intriguing as well. So this is our table in terms of the multiplicative complexity. We've now fixed this lower bound for the field. It actually is 11 semifields. We have one that's 10, we have some that are 11, and there may be some that are 12. So, and everything else is lots of unknowns. So additive complexity in my last minute, I'll just give you a very quick idea. So much less is known because it's a much harder thing to do. You can't just find one tensor decomposition and try to optimize the number of additions. You have to do lots and lots of work. So Jean-Guillaume had a previous as an optimizer that can kind of give you a good algorithm, but it's hard to do exhaustive work. So we looked at the order case of 3 to the 4 and 3 to the 5. And what we were able to show was that the field can be, field multiplication can be performed in 30 operations. We can't rule out the possibility it could be done in 29. So here that's the 9 is coming from the multiplications, and then 2 5s and a 6. That 6 could be improved to a 5, perhaps. In the semifield case, we were able to show that we could do it in 30 as well, and we were also able to show that that was the least possible for something using 8 multiplications. So here's again a case where basically maybe it'd be better to increase this 8 to a 9 and then reduce all those 6s to a 5. So that's possible. And it involved basically the key step was showing these codes can have to require at least a certain number of operations in order to implement them. And then for the 1055 case, we've got some partial results. We're still kind of working and trying to pin things down as closely as we can. So nice questions that we remain is basically, can we talk about these linear codes and try to find some bounds on the number of additions needed in general. And can we actually prove whether their semi-fields are definitely better? Okay, so at the moment it's a draw. I want to find one where I can say there's no possible field that can be as good as a semi-field in this particular way. Okay, that's all I wanted to say. Thank you very much.
Thank you very much, John. Any questions or comments to John?
Sorry for speaking at Irish speed.
Well, if not, let's thank John again. Thank you.
Okay, so just perhaps one last announcement for today. So just to remind you, tomorrow we are going to have lunch somewhere, this kind of like a little farm. So if you may consider walking around there, and if so, please feel free to be wearing, I don't know, tennis shoes if you want to, you know, walk around the farm. I mean, whatever clothing you feel it's appropriate. Okay, so that's all. See you guys tomorrow.